So yes, our last talk is going to be Yalun, who is an intern at Edinburgh University right now, who has just finished up a wonderful internship at Edinburgh University, and you're going to be talking to us about stack switching in Wasm SpecTec. Please take it away.
The new extension, as many has mentioned before in this workshop, that's the stack switching extension. And I'm implementing the extension in SpecTec, which has some interesting technical challenges, which I'll show. Okay, so today's talk will consist of, well, some background, and I'll show the way that I implemented in SpecTec now, that is a bubbling semantics, and I'll show some of my thoughts and some of proposals to implement native context in SpecTec. And finally, I'll briefly introduce some other changes to SpecTec that is necessary to make the implementation working. Okay, so first, let's have a brief introduction of how formal WebAssembly semantics is. So for example, consider the expression 1 plus 2 times 3, which is really simple. And in WebAssembly, it's written as I say to the multiply and add 1, 2, and 3, which is great. And actually, as WebAssembly is a stack language, the stack is written as this. It's 1, 2, plus, and 3, and multiply. So it steps to 3, 3, multiply, and steps to 9. And actually, in specification, it's written as 2 rules. So the first rule is we have a C1 and C2, and we have a binary operation. And we goes to C if C is a possible outcome of the binary operation on C1 and C2. That's the first rule. And the second rule is if C1 and C2 has no possible outcomes, for example, it's a division by 0, then it traps. Okay. So actually, there are two versions of the specification. The version shown above is what we call the prose semantics, and we also call that algorithmic semantics. And the version below, we call that declarative semantics. An important difference of the two semantics is that the prose semantics or the algorithmic semantics has an implicit instruction sequence, while the declarative semantics has an explicit instruction sequence. So as we can see, the prose semantics has, well, an assert, 2 pops, and an if branch. And so, for example, the if branch here corresponds to the first rule on below, on the declarative version. So if it is defined, then return some possible outcome. If it is not defined, then trap. So as we can see, each instruction in WebAssembly has an algorithm in the algorithmic version of the specification, but it can have multiple rules in the declarative version. Okay, and let's enter SpecTec. SpecTec is a tooling that allows us to write the declarative version of the specification in text. So, and then we can translate the text specification to both the declarative version and the algorithmic version automatically. So this is work by Dungeon and many other people. presented in PLDI 2024. So the way the SpecTec works is that the SpecTec DSL that I shown before, this DSL, is first passed to an we call it external language EL, which is basically the same as DSL but as a tree, and then it is elaborated into the internal language, the IL, which is still basically the same modular elaboration. And the interesting part is the IL to AL translation, which translates the declarative semantics to algorithmic one. And then from the AL, we get the prose semantics, and oh, sorry, it's a bit blurry. And then from the AL, we also derive an interpreter that automatically interprets WebAssembly from the specification given. Time is not. I'll skip that. Okay, so to introduce stack switching, we need to know frames in WebAssembly. So frames are the WebAssembly concept to implement control structures at runtime. So for example, consider the block and branch instructions. So the branch one here means branch out 2 blocks and skip to the second innermost block. So the branch one here will proceed to C directly, skipping over A and B. Okay, let's consolidate a bit. So, in the stack, it is like this. The rows of the blocks and the branches are on the above. So, to execute the 2 blocks, we first translate the block, transform the block into a label, which is a frame, which we call it a frame. So, and the outer block is translated into a label. The inner block is also translated into a label. Then the branch instruction get bubbled out. So the branch 1 get escaped from the innermost label, which becomes a branch 0. And then since the branch 0, it escapes the label and brings out the returning value, which is either you got the const 0 and skips to C. So label is a kind of frames, and there are other kinds of frames for exception handling and for function calls. And these frames are what we call administrative instructions, which are instructions that present only at runtime, but not at in the source level. And it is only present at runtime for the declarative semantics. Okay, and with the background of frame, we can finally introduce the semantics of stack switching. So stack switching, well, is switching stacks, right? So there's a continuation part in the WebAssembly store that contains a lot of possible continuations that we can resume. So when we execute the resume, we introduce a prompt frame, which is the temporary name by the way, and move the stack into this. So we move the continuation from the store into the actual stack. So let's see, as you can see, the red box is moved into the stack. Oops. And this is the resume process. And for suspend, we have the reverse process. So first we have a suspended marker, and we move the stack outside the real stack into a temporary area. We replace the suspend instruction with a hole because we do not need the instruction anymore, and put it into a continuation area. And since we are handling the tag here with the label, we replace the prompt instruction with a branch to label with a reference to the continuation. So that is basically what stack switching is doing. The way that I implement stack switching is a way that I call a bubbling semantics. So the bubbling semantics is just like the semantics of the branch instruction that I introduced before. So the branch instruction is escaped from the innermost frame all the way out to the outermost frame that it needs to escape, one by one. So it's bubbling. But the original proposal defined the semantics in a different way, which is defined in context. Context is not a new concept in the WebAssembly specification. It is used to define a lot of things. For example, also the branch instruction. So for the branch instruction, we have the block context, which is basically a hole surrounded by, so it can be a hole, or it can be a context surrounded by a stack and a sequence of instructions, or it could be a context surrounded by a frame, a handler frame or a prompt frame. So with context, we can simply, specify the semantics of the branch instruction as, well, to branch out L blocks, we can just branch out L as the count of the label frames. So the superscript here means the number of label frames to escape. So as you can see, I've made a typo here. It should be K here, not K plus 1. So the K here means the number of labels to escape. But without context, we have to write every kind of frame one by one in separate rows. And this have to be repeated for every instruction that needs to escape these kind of frames. So that's not very good. Contexts are also used extensively in stack switching. This is a context as used in stack switching, which is really similar to the block context. But one important difference is that this is the semantics of the suspend instruction. So as you can see, when we match a handler context, we need to, after we match it, we need to store it into the store. So in the specification, we store the context directly in the store as a component of the continuation. So we need to reify the context, probably not as a tree. So my implementation was to make the context a list of frames. So for example, consider the instruction sequence below. We have a stack of values, we have a frame, and we have an instruction sequence at the end. So the context is defined as, well, the red part is the first frame and the blue part is the second frame. Well, which is basically what is the context. So in my implementation, context is a list of frames. You can definitely also define it as a tree, but being a list makes it easier for the implementation. Okay, it's my implementation now, but it's really kind of ugly because you have to write a lot of repeated code here. So you see, we have a lot of repeated rules, but with context, we can write these rules in one rule. So we're thinking about introducing native context into SpecTec. So in SpecTec, we can just write contexts instead of writing bubbling semantics. So to recap, the architecture of SpecTec is like this. So the important part is the IL to AL translation, or we call the animation pass. But the internal language is the declarative version of the semantics. So it operates on a sequence of instructions. So the design that we are pursuing now is to have a variant of the internal language without context. That is only for the IL backends, the theorem provers, and a future potential IL interpreter. And another translation directly from the IL with the context to the algorithmic language, which is without primitive context. So we have two transformations that remove context from the language. One is the IL to IL pass, and one is the IL to AL pass. We do that because the execution model of the IL and AL makes it pointless to use the same transformation for the sugaring of contexts. So, and for the IL backends, some might claim that supporting context natively for the backends, especially the theorem prover backends, will pose a challenge for the backend. So we might want context to be processed before the code enters the other backends. So we want an IL variant without context. And the design that I'm currently pursuing is to generate a match function for each use site of the context. So for example, we consider the block frame that we've mentioned before. Oh, sorry, is k not k plus 1. So this is the rule of the branch instruction, right? So ignore the colors for a bit. So what this does is, well, what we need to do is, when we meet a branch instruction, we count the number of blocks to escape, which is L here. And we match L blocks out, and well, L labels out, labels as a frame, and then match the L plus 1's label, and then consider the number of values to capture, and then capture n values here. Oh, yeah, the k must be equal to L. Yeah, okay. So that's what's happening actually in the implementations, but in the IL sense, what's happening is we are matching these instructions with this pattern. With this pattern. So we're matching a pattern with n values and a branch with I don't know how many blocks. So the blue ones here are the outcomes of the match function, and the red ones are the inputs. Sorry. What's happening? Okay. So the match function should be like something like this, which is this is a type signature. So we receive a number of values to capture, and we receive the instruction sequence to match, which is the red box here. And we return the number of labels, which is the k here, the context itself, the values that are captured, and the number of branch, and the index or the parameter of the branch instruction. So in this way, we can capture, or to say, we can match a pattern and not a concrete instruction here. So I'll declare that a context is a ADT plus a match function. well, time's up. So, but there are other changes to SpecTec. They are necessary, which I will skip. To summarize, I've implemented the stack switching proposal in SpecTec, and there are some changes that needed to make the implementation work. There's a possible design for a native context. And the takeaways are, so having context in SpecTec is quite beneficial. And automatically transforming declarative semantics to algorithmic is hard. And automatically transforming context to bubbling is also hard. And the SpecTec implementation is designed to work with current spec, not work with future extensions. So it might need extensions for future proposals, and it is fragile. But anyway, try SpecTec for your future proposal. Thank you.
Thanks so much. Any questions? So I imagine that with the approach of generating extraction functions from the context definitions, when you turn that into the interpreter or the prose semantics, do those extraction functions show up in the semantics at that point? Or do you try and handle them a different way?
No, we handle that in a different way as in this picture. So the transformation in the next slide, these transformations are only for the IO to IO pass, not for the IO to AL animation pass.
So if you do have a context in the rule and you want to animate that, do you need to do something special if you don't have the extraction function to make it work?
I think there's no general way to do that. So I implemented in a rather ad hoc way. So a bunch of heuristic and pattern matching.
I can ask a second question. Do you think evaluation contexts are going to get even more complicated in future?
Yes, I think with the introduction of more frames, we already have exception handling, we have effect handlers or stack switching, and there should be more frames in the future as more control structures.
Well, the one I was immediately thinking of was concurrency, potentially.
Yeah.
Cool. I think that's great. Let's thank Yalun one last time.